Hello again to the project Amor, ICMI Awardis Multimedia Online Resources. This module, like its predecessor, is devoted to mathematical objects. In the previous module, I presented a cognitive answer to the question of what mathematical objects are and why we need them. In this module, I will ask how these objects are constructed in general and how students construct them for themselves. Let me begin with the first of these issues. How are mathematical objects constructed? Yet before I begin, I have a promise to fulfill. I need to return to the thought experiment I asked you to perform last time. The exercise, just to remind, was this. Suppose you cannot say number words such as 1, 2, 3, and so on, except in counting. That is, you cannot use these words as signifying anything but themselves. How would you then express what the following equality says? 3 plus 4 equals 7. I suggested you give some thought to possible answers. Hope you will now be able to compare your ideas to mine. And let me present my response. If I was not allowed to say things like 4 marbles in the box or 4 plus 3 equals 7, I could only use number words as empty signifiers, I would probably express the general fact presented here in mathematical symbols as follows. If I have a set so that whenever I count its elements, I stop at the word 3, and I have yet another set such that when I count its elements, I stop at the word 4. And if I put these two sets together, then if I count the elements of the new set, I will always stop at 7. Long, isn't it? This is really a very long sentence. Without condensing this important mathematical truth into the objectified brief expression 3 plus 4 equals 7, how would we be able to develop mathematics at large and its numerical algorithm in particular? This example shows with particular force how the discursive device called objectification impacts the efficiency of mathematical communication by making it possible to say much, much more in much smaller number of words. Let me now return to the question of how mathematical objects are constructed. We spoke about two discursive transformations that constitute the process of objectification: nomination and alienation. I will now focus on nominalization, the process of replacing portions of text with a noun. Let us take a look at the different ways in which we can do this. One of these ways has already been exemplified. I have shown the process of how the process of counting may be turned into a mathematical object called number. Brief utterances with words such as 2 or 5 used as nouns may now replace long statements about human actions, such as, when I count the sides of polygon, I arrive at the word 5. This move of replacing stories of processes with stories of objects is called reification. Reifying is what I do when instead of speaking about my own action of multiplying, as in the narrative, when I multiplied odd number by itself, I get odd number, I can tell a story of an object, of the square of odd number. Like here, the square of odd number is odd. It is also notable that the use of reification is not restricted to mathematics. We apply it everywhere, even in everyday talk. I reify, for instance, when I replace the story employing the verb move, as in the antelope moves fast, with the one that uses the noun movement, as in the antelope's movement is fast. So reification is one way to nominalize, but there are more. Another nominalization transformation that may lead to the emergence of a new object expresses itself in endowing several different objects with the same name and, as such, may be called saming. Saming is what we do when we refer to things as different as, say, dog and cat, with the same word, domesticated animal. We are saming in mathematics when we refer to both the expression x squared and the curve known as parabola with the same name, representation of basic quadratic function. Finally, there is the operation of encapsulating, of replacing the plural form with the singular. This is what we do when, instead of saying the post office workers are efficient, we declare the post office staff is efficient. Here, the word staff encapsulates the workers in singular, and here the workers is in plural. And in mathematics, we are encapsulating when, for instance, we replace the claim the cubes of numbers are increasing with the function x to the third power is increasing. The function x cubed is increasing. While constructing mathematical objects, we perform saming, reifying, and encapsulating in different combinations. Let me illustrate by showing a construction of the object called basic quadratic function. It is reasonable to conjecture that the idea of this function emerged when people realized that some useful stories about the expression x squared may be translated into narratives about the curve called parabola, and also into ones about a certain table of values. For instance, the claim that 0 is the smallest value of x squared can be translated into the story of the smallest number in the lower row of the table and into one of the lowest point on the parabola. Replacing all three signifiers, the algebraic expression, the parabola, and the table, with the single term basic quadratic function allows to make all these three statements simultaneously in this single sentence. 0 is the smallest value of the basic quadratic function. Here, we use the new noun function to perform saming of the three original signifiers. What we call basic quadratic function is now a combination of signifiers with the three of them, x squared, the parabola, and the table, constituting realizations of the signifier basic quadratic function. But the process of realizing signifiers with the help of other signifiers is recursive. And the three realizations of the basic quadratic function may themselves be realized by other signifiers. Thus, x squared may be realized as a square of any specific number. It is thus obtained from these specific squares by saming. These square numbers, in turn, are reifications of the operation of multiplying numbers by themselves. Similarly, both the table and the parabola can be realized as the set of ordered pairs of numbers and their squares, with encapsulation as the corresponding transformation. These, in turn, are reifications of the operation of squaring. Our resulting diagram presents the object called basic quadratic function as the name, basic quadratic function, with its realization network. Let me now summarize some of the insights so far about mathematical objects. First, from all that has been said, it follows that mathematical object can be defined as a signifier as, such as word, written symbol, or icon, together with its realization network. We have just seen an example of such construct. Second, we say that the signifier R is a realization of a signifier S if for any endorsed narrative about S, there is a matching endorsed narrative about R. Thus, the expression xx squared is a realization of the signifier basic quadratic function. And 3 squared is a realization of x squared. Third, I can now define abstract object as one whose construction involves reification. So as long as there is no reification, there is no abstraction. Reification is the source of the same as abstracting. More generally, here is a schematic representation of the way in which generalizations of new mathematical objects are being built, generations of new mathematical objects are being built from old ones. The chain of mathematical objects begins with concrete material objects, that is, those whose existence does not depend on whether somebody thinks or talks about them. I call them primary objects. When a primary object is given a name or denoted with a symbol, we can start communicating about them. In this way, atomic or elementary discursive objects are created. Discursive objects are created by naming primary objects. In this third stage, some atomic discursive objects are combined by saming or encapsulating into compound discursive objects. Finally, or perhaps in parallel to the stages of saming and encapsulating, additional compound discursive objects are obtained by reifying processes on previously constructed objects. This last category of objects is called abstract. This is opposed to the first 3 types of objects, all of which are concrete. Another distinction is between primary and discursive objects, between those that exist in the world independently from the human mind and those that exist only in discourse. Finally, I hope this is now quite clear that within this cognitive rendering, all mathematical objects are abstract because, first, they exist only in discourse, and second, all of them involve reification. The main thing we learn from here is that mathematics is an autopoietic discourse. That is, it is a discourse that creates its own objects while telling stories about them. It's interesting. We create these objects as we speak about them, as we go. And now to the last point. If mathematical objects are discursive constructs, children have to reconstruct them for themselves. How does this reconstruction happen? What kind of hurdles does the learner meet on her way, and how does she overcome them, if at all? Some people recall the birth of a mathematical object as an exhilarating event, a kind of epiphany. Here is, for example, the story of the mathematician William Thurston. He said, I remember as a child in 5th grade coming to the amazing to me realization that the answer to the question of what is 134 divided by 29 is 134 over 29. What a tremendous labor-saving device. To me, 134 divided by 29 meant a certain tedious chore, while 134 over 29 was an object with no implicit work. I went excitedly to my father to explain my discovery. He told me that of course there is so A over B and A divided by B are just synonyms. To him, it was just a small variation in notation. Okay, not every mathematics learner is as fortunate as Thurston. Many students have considerable difficulty while trying to construct mathematical objects. A closer look shows that this difficulty may have several sources. First, there's a certain circularity of requirements. Indeed, if mathematical objects such as numbers are discursive constructs, then to build such object, you need to talk about it, right? But to talk about it, you must already have this object. How can you talk about anything that does not exist for you? To put it differently, you are unlikely to make the considerable effort necessary for the construction of a mathematical object without understanding the prospective gains of such effort. Indeed, you need to understand the usefulness of this object. But how can you be aware of its usefulness before you actually use it? Another difficulty stems from the fact that what happens in the process of objectification often appears counterintuitive. Indeed, when you reify a mathematical process, such as that of subtracting a number from a smaller one, and you say that 5 minus 8 equals minus 3, for example, you claim that there is a product to the operation that has been considered so far as giving no result, indeed as forbidden. And yet it is difficult to say where this new number, in this case minus 3, came from. It appeared with the introduction of the new signifiers minus 3. This new signifier reified the process of subtracting. But this move seems counterintuitive. Indeed, it is not much different from reifying recipe for a cake, from claiming that the recipe is the cake itself. Such cake, as our claim about it, is certainly difficult to digest. In the light of all that has been said so far in this module, the abstract objects that populate the universe of mathematics constitute extensions, in a sense, of concrete objects. They constitute extensions of concrete objects, just like the fantastic beasts to be found in the Harry Potter's world constitute extensions of ordinary humans. Both types of extensions exist only in words, and it is difficult to believe in either. As discursive constructs, they are free to have properties that contradict what we know about the real world creatures that inspired them. Thus, J.K. Rowland's beasts ride brooms defying the laws of gravitation, and they can make new things appear out of nowhere. In mathematics, an infinite proper subset of an infinite set may be considered as equal in its size to the set in which it is contained. No wonder Georg Cantor, who was the first mathematician to come across this strange property, famously exclaimed, "I see it, but I don't believe it." One cannot expect the learner to receive these strange mathematical creatures without an even greater incredulity. In the view of all this, it is not surprising that the student may struggle to construct mathematical objects for herself and that she may take time to succeed. And as long as the success refuses to come, she may have a considerable difficulty benefiting from what her teacher does or says. Indeed, while in the classroom, the teacher juggles mathematical objects. But as long as the student fails to see them, the teacher's movements make no sense to her. Obviously, the question now cries to be asked how to support the student in coping with all these hurdles on her way to mathematical objects. How to help her overcome the circularity and counterintuitiveness of objectification. To begin your way toward possible answers, please proceed to Module 6 of my unit on cognition. Thank you.